hemisphere, not a sphere.
Yes.
And what is the dimensions again?
Radius is 2 meters, and theta is between 0 degrees and 90 degrees.
And, oh, so I got it wrong now. So he's saying, got a sphere, and theta is between 0 and 90?
Yes.
Well, actually, I did have it drawn right. It's this. It's a dome, like so. And what this is the upper hemisphere. This is X, Y, and Z. We're talking about the upper hemisphere. Can you all imagine that? Just take a globe and cut it in half and talk about the upper portion of it. So if we're doing this, there's a couple of things we have to do to make sure we understand this. First is we have to find a differential surface area on this portion that's constant R. Just think of the top of a globe, cut a globe in half, and if you're on the outer portion, you're really at a constant radial distance, right? And when you talk about a differential surface here, ds, remember differential surface has direction and magnitude, right? Now this is in spherical coordinates. So the differential will be r d theta coming down from the North Pole down towards the South Pole. And then the swath will be r sine theta d phi. So the differential is r here. And really, I'll do it this way. It's going to be r d theta times r sine theta d. Maybe I should write this larger. So it's r d theta times r sine theta d phi. Now that's the differential. Just think of the windshield wiper arm thing. When you're coming this way, it's r's constant, d theta is the distance it travels. And then when you're going horizontally in this direction, you have to take r sine theta, is the projection onto that circle of a reduced radius, times d phi. Now it's in the AR direction. Do you all agree with that? That's the surface, differential surface on the outer part, correct, class? Now, when you look at the differential surface on the lower part, this gets a little tricky. And maybe I should try to draw it like this. If you think about a surface, and this would be this cut, this hemispherical cut, but I'm now at the flat part, all right? First, when you take a look at a differential surface here, it would have the dimensions of dr in this direction. Can you all imagine that? Are you with me, class? It would be dr, and then in this dimension here, it would be r d phi. This might be a little hard to see. I'm going to look right up from the South Pole towards the north. I'm trying to draw this. So just assume that the globe would be, the top part of this hemisphere would be into the border. Can you all imagine that, class? And I'll just put the axis like this so you can see what I'm doing. If this is x and this is y, I need a differential surface, right? So I'll just take some lines out here. So if we take a look at a differential surface, we know we're going to have a radial thickness dr. It's got to be a differential. You all with me on that? Now the wiggle in this direction would be r, and then if you're in the xy plane, it would be r d phi. Can you all imagine that, class? That's the differential right there. The direction would be what? Now this is important. Well, obviously be straight down, right? Straight down would be AZ normally, right? Isn't that right, class? Can you all see that? If you cut it in half, the bottom part, if you took a normal, unit normal from the closed surface, it would be downward, it would be minus AZ. Can you see that? But we're not in XYZ coordinates, we're in spherical coordinates. So what vector points straight down that way? Well, this would be A theta, all right? If you think about theta, just listen to me, all right? These unit vectors are tricky. So I'm gonna take my lever arm R, have it straight up, and when I wiggle it, you all see A theta is like just about AX or AY, right? You all see that, class? Now, is the angle between the vertical axis and this radius vector gets larger. That angle is theta, if you can imagine. Now if I stop here, this is the direction of the unit vector a theta. Can you all see that? Finally, when I'm at 90 degrees, it's where that cut occurs, right? Now it's pointing straight down. Do you all see that, class? It's important you do. So this differential here would be dr, or r d theta times dr, but it would be, I'm trying to show you here, this differential surface right here would have a magnitude of r dr d, or r d phi, and then it would be dr, but it would be in the a theta direction. Now that's not intuitively obvious until you look at this carefully. How many see this right here? It's important you to have a good understanding of that unit vector's direction. All right, so there's two, yeah.
Since it's pointing straight down, it couldn't be in the negative AZ direction?
Well, we're in spherical coordinates, aren't we? You could look at AZ's transform, and that's what you're going to get. It's going to be actually the sine of theta, a theta, is going to be the one that actually survives. So it is in the a theta direction at 90 degrees, when theta is 90. Okay, now, when we do this, we have to do the vector integration of this over the surface. Now I want to do this correctly. This is a great problem, by the way. You picked it. I didn't collaborate you before this, but about the problem. But this is a great problem. So what I'm going to do is this. The first integration, when we integrate d dot ds, it's over the entire surface. First surface integration is going to be over this flat area, xy plane. With me, everyone? So when I do this, I'm going to say really the integral of d dot ds over the closed surface S is really the integral of d dot ds, and this is going to be over, call it the xy plane, plus the integral of d dot ds, and I'll call it over the top hemisphere, right here. So I'm going to do this one. I'll label that 1, this 2. Do that one first. So that integral of d dot ds, right here, well, d is given, right? Now, look, ds for that one is really going to be r d phi dr. I'll put the differential first. I'm sorry, it's, yeah, r d phi dr, and it's in the a theta direction. Isn't that right, class? That's just the differential on the bottom of that, the lower cut of the sphere. Y'all see that? Now, when I dot this in with this unit vector, I want you to, or with D, I want you to take note. I could write every one of these terms, couldn't I? But what is AR dot A theta? Class? What is AR dot A phi?
0.
It's 0. What is AR dot A theta?
0.
What is AR dot AR?
1.
1. All right, now the only one that survives would be A theta dot A theta because they're the same unit vector, right? When I dot A theta into AR, it's 0. A theta into A theta, it's 1. A theta into A phi, it's 0. So the only term I'm going to put there is going to be this term. Can y'all follow me? Right? I could write every term, but the other two dot products, the dot product would get rid of that one and that one, wouldn't it, class? So I'm just going to put minus cosine phi A theta. And I know the other dot product is going to be 0. That's a dot product right there. Right? Well, what is the dot product of A theta, A theta? We just covered it. 1, right? So, y'all agree with me? So I'm just going to get rid of it. Now, that's what I have to deal with. So my next step is setting the limits for this integration. Where does the theta go from? Theta is the xy plane. It's a vector, right? If you measure theta from, you start at the x-axis and you measure to the projection of the r vector in the xy plane. So it can go from the x-axis all the way around to the x-axis, or 2 pi. You all see that?
That's phi, right?
I mean phi. Did I say? So d phi, my bad. So from 0 to 2 pi would be the phi integration, and I better put that. Yeah, I can do that. 0 to phi would be phi integration, and where does r go from? So over the entire flat bottom surface, from 0 to the outer edges at 2 meters, did you say?
Yeah.
From 0, r equals 0 to 2. So what's this going to be? Well, this is minus right there. And I'm going to take the dr integration first. So when I integrate r dr, I get r squared, right, over to evaluated from 0 to 2. And then when I integrate cosine phi, what do I get? Integral of a cosine, think about this. Well, what do you know? Integrate, a derivative of a sine is cosine, right? Integral of a sine is minus cosine, right? Is that right? Integral of a cosine is sine, isn't it, class?
Yep.
So this would be just sine of phi, and it would go from 0 to 2 pi, correct? Isn't that right? Y'all agree with me? Now, second. Now, here's what's interesting about this. This is the integration of a cosine, right? Over a range from 0 to 2 pi. What do you know a trig function integrated over a period? Oh, I mean, it's cosine of sine. What's the integral of a sine over a period from 0 to 2 pi? Just sine that, huh? 0. What's the integral of a cosine from 0 to 2 pi? 0. The area above the 0 axis is the same as below, correct? This goes away. I don't even need to do that integration. That goes away, which is nice. Do y'all follow me? This is a typical Whitworth trick. He's going to find, people will find a way to get something non-zero there, but it's 0, okay? And it's because that's a cosine right here. Right? Cosine integrated over 0 to 2 pi with or without a minus sign in front of it is still 0. Now, the only integration that's going to survive is this outer surface. All right? So when we do the outer surface integration, and I'll do that here. So when I integrate d dot ds over the outer surface, or the hemisphere, now that's the integral. And just think about that. First I'm going to put the differential. So that's r squared d theta d phi, I mean sine theta, pardon, r squared sine theta d theta d phi in the AR direction, right? This is going to be a double integral. But it's a dot product. Now I have to take that ds and I have to dot it into d. But what do you notice happens? Now it's just like the last part, or the prior part. Well, that's an AR, right? Y'all with me? Do I have to worry about AR dot A theta? What is AR dot A theta? 0. What is AR dot A phi?
0.
So those two I ignore. I could write them, but then I'd have to ignore them. I don't want to do that. I just don't want to write them. So I'm just going to put the first part, 3R AR. Right? And then my next obvious step is AR dot AR is 1. So I just erase it. This is, I'm trying to get you familiar with noticing the obvious and taking advantage of it, so you don't write things down for no reason. All right? So now I have that. Now, I have a d theta d phi, right? Where does theta go from? Remember, theta is measured from the z-axis to the radius vector r, right? It can go from 0 to pi, correct, class? But how far is it going? From 0 to pi over 2. Do you all follow me? So here, my theta integration right here goes from 0 to pi over 2. What about my phi integration? Class? 0 to 2 pi goes all the way around again. And this would be the flux. The integral of d dot ds is called the flux. They use this symbol, psi, for flux usually. I put that down in the one note. Are you with me, class? All right, now work with me. You'll notice there is no dr integration, right? So that 3r squared times, or 3r times r squared is 3r cubed, isn't it, class? That comes right out in front. Now, the next integral is going to be the sine theta d theta. What is the integral of sine theta d theta? We just covered. Minus cosine, isn't it, class? So it's going to be minus cosine theta, and that's evaluated from 0 to pi over 2, right? And then we got the phi integral from 0 to 2 pi, which is just what? When we integrate d phi, we get phi, right? Evaluated from 0 to 2 pi is just 2 pi, right? Now I know r is, what was it, 2 meters or something like that?
Yes.
We'll put that in last. So what happens here? Well, this is the way I like to do it. You see I got a minus something, and I'm evaluating from the lower to the upper. To get rid of that minus sign, I switch the limits and get rid of it. All right, so I can make that, get rid of that, make this 0, and make this 2 pi. Or pi over 2, pardon me, pi over 2. Y'all follow me on that? I'm just trying to make it easier on myself. Now when I look on that, at that right there, what is that? Well, I got 2 pi times 3r cubed, so it's 6 pi. And it's r cubed. And what about cosine evaluated at 0? What is that? This is, now I'm doing the cosine evaluation. Cosine of 0 is 1, right? Is that right? Cosine is, it's easy to make mistakes, but get used to thinking through these things. What is the cosine of pi over 2? 0. So if I'm just multiplying that by 1, that's it, isn't it, class? And now I'm putting the value for r, which is 2, correct? Isn't it? So this is going to be what? I got 2 cubed, or 8 times 6, or 48 pi. And this would be coulombs. Now, is that the answer? I don't know what you put down.
I think so.
Is that it?
It is.
Should be. That's a standard Dr. Winkler problem, I can tell, because he knows that he's just going to zero out one of these integrals. He doesn't want to mess with it. But he wants to give you one that makes you think, and that's a good one, right there. Is it the right answer? Okay, thank you for that question. That's an excellent question. But I want to do one that uses this is really just evaluating a flux integral. Whenever you integrate d dot ds over any surface, it's called a flux. The symbol for this is psi. That's it. They just chose that symbol. Why? I don't know. Anybody here in fraternity? Yeah.
That was units of
Coulombs. Right, right. And if you integrate the flux over the entire surface, and integrate d dot ds over any closed surface, it's the charge enclosed. And it better be in coulombs. All right? Now, that's a good problem because it makes you think about integrations over surfaces where you have to get the differential surface. And that's always a problem in this class because you don't have a rigorous course where you have to define differential surfaces in math. I don't think you do. All right, you've had integral calculus, but you didn't have vector calculus. Vector calculus is what I took when I was where you sat. And that is something. They force you to come up with differential surfaces for all sorts of bizarre surface areas. Here, this one establishes the fact you have to understand it if you want to do it right. You have to understand the differential. I want to do one with Gauss's law in the pure form. You want to pick one for me that I assigned? We can do the last one if you want, the one I gave you. Because that's a good problem. On purpose, I gave you that. That's actually from an old quiz, so it gives you an idea of the level of difficulty I expect you to be able to handle on the quiz. This stuff.
I think 3.35 might give what you.
You want to do that one? Okay.
Do that one, this one.
You want to do 3.35? We'll do that.
I think it's.
All right, go ahead, give me the specifics.
It's a spherical charge density is given by rho v equals rho AR divided by A.
Rho, not?
Rho v
Oh, volume charge density, so that's the density, rho v, times, go ahead,
rho AR divided by A.
times what? You said spherical, right?
Yes, spherical charge density.
So rho v times what?
AR
Times AR.
divided by A.
There's no R in here? That's it?
Oh, excuse me, I'm reading it wrong. It's rho A times R divided by A.
Rho v times R, right, okay, that makes sense. So it's rho v, which is the volume charge density, times R, and this is divided by A, right? And it's not a unit vector, this is a scalar, right? That's the volume charge density from where to where?
Yes, from 0 to A.
That's what it is, yeah.
And then,
Zero else?
yeah, rho v is also 0 for R greater than A.
All right, so rho v equals this for R between, I can do it this way if you'd like, between R greater than or equal to 0, less than or equal to A, and then rho v is 0 else, basically, anything greater than that. So that's up, go ahead.
I think the expression is rho v is equal to rho A.
Rho A?
Times R over A.
Okay.
Yeah.
Rho sub A.
Rho sub A.
All right, it's a volume charge density. Doesn't matter what symbol you use, it's a constant. If we're gonna do this, basically what we have, it's important you see this, we've got something, we got a sphere of a radius A, and this is where all the charge is. It's inside that sphere. It's distributed according to this distribution right there. You with me? And we have two regions we have to worry about. We have to worry about the D field for R less than A and then R greater than A. So we start with the first one. And this, we're going to go from R less than or equal to A. If you want to put greater than or equal to 0, you can, but it's not necessary. And so when I'm doing Gauss's law, this is something you're going to always do. Right off the bat, you write down the general formula. The integral of d dot ds over any closed surface is equal to the integral of, it's really the charge enclosed. In this case, it's going to be the integral of rho v, the volume charge density, over the differential volume. Now, that's just the general formula that works for any coordinate system. Now we're going to use the specific coordinate system's values and put it in there. When we do that, well, the integral of d dot ds, remember we're inside the distance A. Now we draw this thing up here. I'm going to show you pictorially what the surface looks like. So I basically have a sphere of a radius r, and I'm looking at the integral of d dot ds over that sphere. So the D field has to be assumed radially outward, and that's what I'm trying to indicate there. It's radially outward. In the integral of d dot ds, now just listen to me, the D field will be in the radial direction. You have to be able to see that. One of the reasons why I can make an argument for it, you see how this is a spherically symmetric distribution? If you take a ball with this distribution and you rotate it over any phi or theta, it looks the same. Y'all follow? There is no theta or phi dependence, so it's spherically symmetric. And if it's spherically symmetric, the D field, you argue this from symmetry in some cases, has got to be radially outward. Y'all with me, class? Now, I'll only do this one time. Please don't write this down. Just listen. When I take the integral of D dot ds over a spherical surface, what that will be is an integral of dr ar. We're assuming it is in the radial direction times the differential surface of this on the sphere right here. Well, that differential surface will always be, for the spherical surface, r squared sine theta d theta d phi, and it will be in the AR direction. Now just listen to me about this, okay? I've got the D field dot ds, and this is supposedly the dot product right there. Now, when I do the dot product of this, the AR goes away. I didn't show you the other differentials because I know they're going to dot to zero. So AR is going to go away. And now I'm going to integrate d theta from 0 to pi and d phi from 0 to 2 pi. This is going to come out to be the D field in the R direction times R squared. Then I integrate phi from 0 to 2 pi is 2 pi. Integrate sine, I get minus cosine from 0 to pi is going to be equal to 2. It'll be a cosine of 0, which is 1, minus a cosine of minus pi, which is minus 1. So minus 1 is 1. 1 and 1 is 2. So this comes out to be 4 pi. Or I have 4 pi r squared dr. Now what is 4 pi r squared to everybody? It's the surface area of a sphere, isn't it, class? So just remember this. If you have spherical coordinates, and you're doing Gauss's law, and you're integrating over a spherical surface, then the integral of d dot ds will always be that surface area, which is 4 pi r squared, times the d vector, the r component of it. And there's only going to be an r component. Y'all with me on this? Now, on the other side, we're going to have to do this integration. But I want you to listen to me now. That's a differential volume. So first thing, if it's a differential volume, there are 3 coordinate axes we're going to integrate over. So I put down a triple integral. Next, I put in this. Now remember, this is only true from 0 to a, but we're inside of a. We're for r less than a. Y'all with me? We're inside that sphere. So this becomes rho a times r over a. And now I need my differential volume in spherical coordinates. Some of you haven't done a lot of this. You're gonna have to get used to this in a hurry because you're gonna be doing a lot of this in EMAG in one answer. The differential volume in spherical coordinates inside here, if I could draw it, I always had trouble with this one, but basically it has dr this way, it has r sine theta d phi in the horizontal or in the phi axis, and this is always going to be r d theta. Don't worry about that little chunk there. Differential volume doesn't have a direction. Y'all with me? Differential surface does. So this is going to be r squared sine theta d phi dr. And now I want to talk about this. And I want to make sure everybody sees. You all agree with the way I've got that? If you don't know what that differential volume is, look up the notes that I sent you that, I don't know, a couple lectures ago I showed you the differentials in Cartesian, in cylindrical, and spherical. But that's when you got to know. R squared sine theta d phi dr. Now, when we look at this, where's theta going to go from? Theta goes from North Pole to South Pole, or from 0 to pi. So theta is 0 to pi. Now where does phi go from?
0 to 0.
Right, from the x-axis all the way around to the x-axis, or 0 to 2 pi. Right? And where does R go from? And this is important. This is when people trip up on. The normal response I get from about a third of the class is 0 to A. Remember, this is at a distance R. That's called my Gaussian surface. It's fictitious. I'm saying for my Gaussian surface, I'm only out here at distance R, and R can be anywhere from 0 to A. It is not defined at A, right? It could be, but it's not, generally. Y'all with me? It's going from 0 to R. Just like that is the surface, right? R squared, that same R. So it goes from 0 to R. And to be mathematically rigorous about this, now we're engineers, so I don't hold you, but if a math prof was in here, probably yell at me. This should actually be primed, all right? Because you can't integrate something with the same symbol that the limits have. Y'all with me, class? You can't integrate something dx and have a limit from 0 to x, technically. Even though we know this integration, the R inside this integral is really a dummy variable. It could be V, it could be L, it's going to integrate out. So when we do this integration now, here's what I'm going to do. I'll put it down here. First, I always take out the constants. I have rho A over A. Y'all follow me on that? Right, I'm just pulling the constants out of that integration. I don't need them there. Next thing I'm going to do, well, I'm left with, when I do the theta integral, just look here. I can write this down for if you don't see it. I have a sine theta d theta, right? I'm integrating a sine theta. It would be a minus cosine theta. Do you all agree with that? Now this is the trick that I know because I've done this so many times. Anytime I see a sine theta integrated from 0 to pi, I know I'm going to get 2. All right. Sine theta is minus cosine theta, right, from 0 to pi. Flip the limits, I get cosine theta plus cosine theta, right, from what, pi to 0, right? So what's cosine of 0?
0.
1, right? Cosine of 0 is 1 minus the cosine of pi. What is the cosine of pi? Minus 1, right? 1 minus quantity minus 1 is 1 plus 1 is 2. It always is 2. So I know I'm going to have a 2 here, and that's for the sine theta d theta. I can write this down, but it's really kind of a waste of board space if I can talk through it. Now, what happens when I integrate phi? I mean d phi. Pardon. Integrate d phi, I get phi from 0 to 2 pi is 2 pi. Some of you are going to see something here. You always, this is one thing that's so clear when you're doing spherical integrations. If this density, charge density, is not a function of theta or phi, then when you do the theta integration and the phi, you always get this 4 pi. All right? You with me on that, class? I'll get 2 when I do the sine integral, and I'll get another 2 pi when I do the phi integral, always. So there's going to be a 4 pi there. Now I'm left with what? R cubed dr, right? What is r cubed integrated? 1 over 4 r to the 4th, isn't it, class? Right? So now I'm left with r to the 4th over 4. And I can go from 0 to r, but if it's 0, I don't need to put it in there. So I have r to the 4th over r here. And you can clean that up, I suppose. So I can have 4 pi, well, look here. 4 pi, I got a 4, that goes away. And I'm left with what? Rho A over A, right? And then I have times pi, and then times r to the 4th. So that's the integral on that side. On this side, it was 4 pi r squared d of r, right? Y'all agree that last part's the correct manipulation of it? And to help everybody, I'm gonna erase that if you don't mind, that middle part, so I can just talk about the end in this. You with me, class? Can you all see it over there in the back? All right. Can you see it? Okay. Whenever I see a person squint, I try to, can you see this? I mean, yeah, you got it? Okay. If we're good, we're good. So now I get rid of this. Now, just look at this. I want to get D of R, right? Can you all see the only thing I'm going to do is start canceling and moving? I've got pi's on both sides, don't I? Get rid of them. It's nice to do these problems on a board, isn't it? You can just do it. My friends have big whiteboards that are engineers and stuff, especially people that own companies that have to, they do elaborate mathematics to get I mean, whiteboards, they're always erasing and marking and taking pictures of. They don't use paper until the final product comes out. I'm down to here. I guess you could do that though with your iPads these days, right? You can do it with the tablets. All right. Anyway, now the next thing I can see is I got r squared here, r to the fourth, divide both sides by r squared. This becomes r squared, right? Now I have a 4 over there that's unaccounted for. So I divide this side by 4. And that is my d of r for r less than or equal to a right there. Now we're not done with this problem, because now we have to go outside. We have to go for r greater than a, don't we? Isn't that the second part? Here's the one thing I want you to realize. When we go and we have an imaginary, or we have a Gaussian surface, I want you to see this. Now we're going to be outside here. So, now when I'm in the second part, for r greater than a, I'm going to draw the Gaussian surface so you see it. Now I'm out here, and now my Gaussian surface is outside the limits of where the charge exists. You all with me? Now this is so important. Anytime you have a spherically symmetric system, and you want the D field, uses Gauss's law, and you're outside the area, the volume where it exists, the charge exists inside R equal A, all that charge can be just summed together and put right at the origin, and it will look like a point charge. Do y'all follow me? Now I'm going to prove it to you. That's real nice. Believe me, it's real nice. So I come out here, and now I go ahead and I say, well, it's the integral of d dot ds, the general form, is equal to the integral of rho v dv over the volume right inside. This is a limited volume. It goes from 0 to a in the r direction. It doesn't go from 0 to r anymore. You with me on this? So over here, the d dot ds will always be that surface area of a sphere times d of r, dr, right? That's on this side, always, if it's spherical. Everybody understand why? Now, when we're on that side, now I do the same exact thing as I've done over here with one change. My limit goes from 0 to a now, because there is no charge density that I have to worry about. I mean, it's 0 right there when I'm at a distance r greater than a. Y'all follow me? All right, so now the total charge here would be integral from 0 to a, integral, I guess I have 0 to 2 pi, integral from 0 to pi. Over here we have rho a over a. Then we have r cubed, I'm just pulling the r's together, sine theta, d theta, d phi, dr. Okay? And again, look at, that's the same as that, right? So I pull the constants out. So this becomes rho a over a. Then the first integration I'm going to do is sine theta d theta, which is minus cosine theta. Remember doing this? Minus cosine theta from 0 to pi. It's going to be 2, like before, right? And then I get d phi integrated from 0 to 2 pi is 2 pi. So I have 2 pi times 2, or 4 pi. Y'all give me that for the angular integrals? Now, the next part is dr. I have an r cubed dr. It's r to the fourth over 4, correct, class? R to the fourth over 4, but it's evaluated from 0 to a, or now it's simply a to the fourth over 4 on this side. Y'all follow the reasoning behind? Come over here, now I have 4 pi r squared dr. This is a good one. And now what am I gonna do? Besides get a drink of coffee and let you write. Anyway, this is my rule. Get rid of anything you don't need. Cancel it out. Never carry along constants you don't need. So I see pi on both sides. I see a 4 on both sides. Well, actually, there's going to be a 4. I'm going to do it this way. I'm going to get rid of 4 pi because it appears in both sides instead of dividing by 4. You all with me on that? What else happens? Now I divide by r squared, correct, class? And maybe before I do that, you see how that's a to the fourth and a? So I'll make it a cubed. You all see that, class? I'm just going to make it a cubed. And now I have r squared I have to bring over. So that is my D field for r less than, greater than or equal to a. And I've got a comment about this once you write. I'm trying to do this in a way it's not too fast, but I want to cover it so I can make a few comments. All right, when you do that, one thing that's real important to see that 1 over r squared? Well, 1 over r squared is how the electric field falls off from a single charge piece of Q as you go further and further away. So all this charge effectively can be stuck at the origin and just divide that charge by 4 pi r squared, and you will have the D field. You all with me on that? That's a real important thing to kind of get in the back of your mind. When you're doing these problems, don't ever let them scare you. All right, but you're going to be learning about the types of problems and how you can almost read through and know what the answer is before you do it. I know if I can get all this charge, just integrate the volume charge density, stick it as a value Q here, then I can look at that as a point charge. And I know for a point charge, the electric field from a point charge is Q over 4 pi epsilon naught r squared, right? And for the D field, it's just, forget the epsilon, it's Q over 4 pi r squared. That's it. And it's in the AR direction. And that's nice to know because it simplifies things. Okay. Y'all see what I'm talking about here? Please do those problems. Now, for today's remainder 2 minutes of the lecture, it's important to do problems. Some profs don't. Right? They just collect homework and get solutions. They have to go there. If I don't talk through these problems, I don't think you'll see some of the finer points, especially some of the tricky stuff. It always gets people. All right, we were in electrostatics. We just got done with Gauss's law. Please do those problems. The differential form of Gauss's law I talked about, or the divergence form, I'm just going to tell you what it is. Because honestly, when you're doing this, the divergence form, the only thing you do is mathematically use the definition of divergence to do the operation, and you have the divergence of D. But I'm going to do something for you to help you along. So when we talk about Gauss's law, the integral form of Gauss's law is the integral of d dot ds over any closed surface is really equal to the integral of rho v dv over the volume, all right, of that Gaussian surface. And when you think of the integral form, always think of a closed surface S. And think of the D field, all right, that's puncturing that surface. The integral of that D field over the surface will be equal to the charge inside. And you can just call this Q inside. Now that's the integral form, for obvious reasons. Those are integrals. The divergence form is simply divergence of D is equal to rho v. Now, how many of you have had divergence? It is a mathematical operation, and it is defined I can show you them, I mean, Dr. Wentworth's book does this on page 161. But you all have your books with you, or access to them? In the back of the book, there's on the back cover, right here, there's divergence in Cartesian, and cylindrical and spherical coordinates. You all see that? All right. So I'm just going to go through the most simple example of this stuff. Oh boy. I'm going to say the divergence of d, I'm already over by a minute, I know, is ddx of dx plus ddy of dy plus ddz of dz. Now, I just want to tell you one thing. This is sometimes called a vector derivative, I think. There's a term for it. It might not be the exact term, but what it's doing is saying if you have a vector d and I want the divergence of d, it's not Cartesian, it's not a vector, it's a scalar. I simply take the x component, do a derivative with respect to x, y component, do a derivative with respect to y, and z component, derivative with respect to z, and add them together. Now, we can do it for the other two coordinates, but I think I can hand this off to you with some problems, because, yeah.
So this is similar to taking gradient, just the gradient's over.
Now, gradient's a vector. Gradient is a vector. This is a non-vector. Gradient has a vector direction to it, all right? And that's a little different. It does involve derivatives, but a gradient it's a rate of change, but it's a vector rate of change that I don't have time right now. I just want to tell you one thing about this. See how it's equated here? Rho v is always a scalar. That means divergence of d is a scalar. It's not a vector. There are three coordinate systems you have to concern yourself with. Now, I'll give you problems. Then I'll just tell you on Wednesday, Wednesday, this isn't bad at all. What I'm going to do is I'll go through the gradient too, which you won't have any trouble with. And then I'll start at the conductors and Ohm's law. But it's a differential form of Ohm's law. Now, I know this lecture seemed to weigh a lot of time on just a couple of simple problems, but I've tried to underscore some of the things you have to see and understand. Because those problems can get real tricky if you don't see the obvious things. I'll be in my office if you need to see me.